Right, so this is part 3 to section 1.4, and it's just going through more examples. So I'll just jump right into it. Number 7, determine each limit and discuss continuity. And they're saying limit as f of x as x approaches c from the right. So first off, this is a right side limit for part A, or right hand limit. Where it has the minus sign, x approaches c, that's going to be from the left. So this is a left-hand limit. And this is just the regular limit that we're used to, so which I was calling like the overall limit. And then part D is not a limit, it's just evaluating the function at C. So this is finding what the graph is. So finding what f of C is on the graph. All right, and here's our graph. So the graph's in green, and in this case, we're talking about C being 3. So to answer these questions, so for part A, we're talking about x approaches 3 from the right. So that's where the plus sign comes from. It's a f of x. So as x gets closer to 3 from the right side, the graph keeps getting closer and closer to the hole, and that hole is at the point 3, 0. So there's a hole in the graph on the x-axis at 3, and the hole is 3, 0. So as x approaches 3 from the right side, the graph itself is getting closer and closer to the hole. And the hole's got a y coordinate of 0. So we would say equals 0 for the right-hand limit. Now for the left-hand limit, as the x values approach 3 from the left side, the graph itself, the y coordinates are still approaching that same value of the y coordinate of the hole, which is 0. So the left side limit, left-hand limit is also 0. So for part C, for the overall limit, since the left side limit and the right side limit equal 0, so since both the left side limit equals 0 and the right side equals 0, as x approaches 3 from either direction, then we can conclude the overall limit as x approaches 3 of f of x is going to be equal to 0. All right, so that's going to be the answer. It's 0, since the left-hand limit and right-hand limit both equal 0. Now for part D, where it says f of c, so c in this case is 3. So we're trying to see where does the function hit when you plug in x equals 3. And you'll see that at 3, there's this closed dot. That's where you evaluate the function. And the x coordinate of that point, so that's 3, so you'd say f of 3 is going to equal the y coordinate of that point, and that y coordinate is 1. So the function's defined at this closed point, closed dot, and it's got a y coordinate of 1. So f of 3 equals 1. Since we have closed dot, so the dot at 3, 1. Now, as far as the continuity goes, because there's a hole at 3, 0, since there's a hole in the graph, then it's a discontinuity. It's called a removable discontinuity. At x equals 3, right? It's removable because I can, let's say if I took the point 3, 1 and then I moved it down to where the hole is, that makes the graph completely connected. So this is an example where you have the limit equaling a different value than if you were to evaluate the function itself for that same particular value, fixed value 3. So I'd say notice these come out to be different values for the y coordinates. So these are different. All right, f of 3 is 1, the limit is 0. All right, so that's that one. Now, the next couple examples, you're going to find the following limits. And anytime I'm finding these limits, doing analytical approach, you try to plug in the x value or the value which you're approaching the limit. So for number 11, so this is technically a right-hand limit as x approaches 8. So, but instead of having to graph it, I would just try to plug in the value for x. So if you plug in 8, just like if it was a regular limit, so this is number 11, plugging in 8 gives 1 over 8 plus 8. So 1 over 16. All right, that's what the limit's going to be as x approaches 8 from the right. And you'll see it's the same thing as x approaches 8 from the left. So I still just plug it in. So try plugging in the value first. Now number 13. All right, so if you did plug in 5, all right, this will give you 5 minus 5 over 5 squared minus 25. It's going to give you 0 over 0 indeterminate form when you plug in 5. So try to do some factoring since I have an x squared minus 25 on the denominator. So the denominator changes into x minus 5 times x plus 5 if you're to factor that. And then the x minus 5's divide out. And just as a comment from the previous video where we dealt with continuity, discontinuities, when this common factors divide out from the numerator and denominator, that means there's a hole. And specifically, it's going to be at x equals 5. All right, even though there's a hole at 5, that doesn't mean that the limit doesn't exist. But that's just a comment. There's a hole at 5. Do the common factors dividing out. So after you cancel out common factors, that's going to be 1 over x plus 5. And then you just try to plug into 5 now. So that's going to be 1 over 5 plus 5, which will be 1 over 10. So the limit's 1 over 10 as x approaches 5 from the right, even though there's a hole in the graph at 5. All right, so number 15, this was supposed to be x approaches -3 from the left. All right, so we're approaching -3 from the left. And if you plugged in -3, you get -3 up top. On the bottom, there would be the square root of -3 squared minus 9, which is going to be the square root of 9 minus 9, which is the square root of 0. And you get -3 divided by 0. And you can't divide by 0, so this is undefined. So we need to see, can we still determine the limit, even though when you plug in -3, it's undefined. And to do this, what I would try doing, so because of the square root, there's really no common, I can't really do any factoring to cancel out common factors from top and bottom, since the top does not have a square root. So I can't really do any factoring to our advantage. Now you could try rationalizing, I suppose, but I think that also will make things more complicated. And whenever I run into something like this, where it's complicated to do the factoring and very complicated to do the rationalizing, I would try just looking at its graph to see if we can determine the limit from the graph. So try graphing. So I'll pull out the calculator and show how I would graph the function f of x equals x over the square root of x squared minus 9. All right, so the TI-83 graphing calculator is what I'll be using, and I'm graphing the function x over the square root of x squared minus 9. And from its graph, I'm interested at the limit as x approaches -3 from the left side. So when I go to y equals, and for y1 equals, I'm going to type in, so I press this button for x, and then division, and then the square root. So I'll do second, then x squared button because of the square root signs in yellow directly above the x squared button. So if you hit the second button first and then x squared, it'll choose the square root versus the square. Now I'm going to type in x squared minus 9. And make sure to enclose the square root with parentheses. And now I'm going to hit graph. And you'll see the graph looks like it cuts off right here. It's very kind of deceiving because, and that's pretty close to -3, but instead of it actually stopping right here, it goes down forever, like there's an asymptote. And if I plug in, like if I hit trace, type in -3, it comes up blank with the y value. Now, if I'm approaching -3 from the left side, let's say I did -2.99, or sorry, -3.011, because that would be coming from the right side. So I want to come from the left side of -3. So I'll try -3.01. And you see that I have a y coordinate of -12 something. And notice it doesn't appear in the window. I'm not sure why. It's just the calculator software doesn't show that this goes down forever. But you can see that the y coordinate's -12.27805 when I plug in -3.01. Now my window of view goes from -10 to 10 for x and -10 to 10 for y. But really all I need to do is focus on just get a general feel for what the graph's going to be, and then see what the, I guess you can hit trace and see that the y coordinates will get really big. So if I tried -3.001, you see it jumps down to -38 point something. And I keep hitting trace, and then let's say I did -3. Keep getting closer and closer to 3. You see that jumps down to -122 point something. So really this graph goes down forever and then jumps to here where it looks like around 3. There's another vertical asymptote, and it should probably shoot up forever and getting closer and closer to 3. And there's nothing in between. So if I were to sketch its graph, it would look something roughly like the following. So I'll use red dashed lines for the asymptotes. So let's say this is -3. Let's say that's 3. Now the graph doesn't show you these dashed lines in the calculator, but these are going to be the asymptotes. And around -3, coming from the left side, I'll use blue for the actual graph. It does something like this. It'll shoot down forever. All right, and the graph sort of cut off. It didn't show this indication that it was going down forever. That's why I was typing in values for x and getting the corresponding y values, which kept getting more and more negative as I was getting closer and closer to -3. And then there was nothing in between. And then the other part of the graph was doing something like this. All right, so that's what its graph looks like. Now we can look from the graph and answer a question as far as what is the limit as x approaches -3 from the left side. So from its graph, as x approaches -3 from the left, the y coordinates go down, the graph goes down to -infinity. So the limit is technically -infinity, but it's not a finite value. So I'd say limit as x approaches -3 from the left, and our function was x over the square root of x squared minus 9. That's technically -infinity. It's not a finite value. So I would accept saying it's -infinity, or you could say that since there's not a finite value, there's no finite limit exists. And that's how I would handle this question, and hopefully it makes sense why I can't really do any factoring to my advantage because of the square root sign. I couldn't cancel any common factors to simplify it any. And it might have been more complicated to rationalize if I were to multiply top and bottom by the square root of x squared minus 9, because then it'll still give me 0 in the denominator. It won't help me at all because I'll be left with what's underneath the square root, x squared minus 9. So plugging in -3 still gives me 0. It's just not having the square root. So that wouldn't help either if I rationalized. So that's why I resorted to graphing. So if all else fails, I would try graphing and see. And really, you couldn't be able to determine this without graphing. You'd have to see that it shoots down to -infinity, coming from the left of -3. Now, there's no portion of the graph that is to the right of -3. There's nothing in between the two vertical asymptotes. Okay, so that's that one. That was number 15. Number 17 is the absolute value of x over x as x approaches 0 from the left. So from previous video, I did an example with the absolute value, and the definition of absolute value is really a piecewise function. It's equal to x if x is greater than or equal to 0. It's equal to -x if x is less than 0. In this case, x is approaching 0 from the left side. So since I'm approaching 0 from the left side, all of the values to the left of 0 are negative. So all the values to the left of 0, like on a number line, are negative. They're less than 0. So less than 0. So really, when I find this limit, and it's a left-hand limit, since my x values are approaching 0 from the left, they're less than 0, which means as far as the piecewise function, I'm only dealing with this piece, since we're dealing with x values that are less than 0, since approaching 0 from the left. So this will equal, plugging it in, definition, so limit x 0 from the left, and that's going to be negative x over x when x is less than 0. And in this case, we're approaching 0 from the left, so that is what we're dealing with here. That's equal to x divided by x is going to cancel each other, so you're just left with negative 1. So this equals negative 1. All right, so that's going to be the answer for that one. And the previous video, and I talked about its graph, it looks something like the following. So here's 1, here's negative 1. There is a hole at negative 1, or at the y-axis at negative 1, and it was a horizontal line. And there's a closed dot at this, and it was a horizontal line in that direction. If we're talking about x values to the left of 0, approaching 0 from the left, they're getting closer and closer to the hole, but all of the values on this line are the same. They're all negative 1. So that's why the limit from the left side is negative 1. All right, so that's number 17. The next one is this piecewise function. And I think I'll do this off to the side. So they want to know what's the limit as x approaches 1 of this function, where it's broken up into these two pieces. And since this is limit as x approaches 1 of f of x, this is the overall limit. Now the overall limit exists when the left-hand limit equals the right-hand limit. So this exists when the left-hand limit equals the right-hand limit. So I would find the left-hand limit and right-hand limit and see if they equal each other. Since we have two pieces, we want to know for each piece what the limit is, and depending on which direction we're coming from dictates which piece to use. So find the left-hand limit, and as a that'll be limit x approaches 1, and since I'm coming from the left, it'll have that minus sign of f of x. Now these are x values that to the left of 1, they are values that are less than 1. So this is involving x being less than 1 if I'm approaching from the left. And if I'm approaching from the left, or x less than 1, I'm only dealing with the top piece, x cubed plus 1. All right, and I just plug in 1, see what that gives. So that's going to be 1 cubed plus 1. All right, so equals 2. So the left-hand limit's 2. All right, now I'll try to find what's the right-hand limit, and I'll use a different color. So I'll use green. So find the right-hand limit. If I'm approaching 1 from the right side, that means I'm dealing with values of x that are greater than 1. So really I'm going to be involving the bottom piece. So if this involves x values that are greater than 1 if I'm approaching 1 from the right side. So the right-hand limit since my x values are greater than 1, I focus on the bottom piece, x plus 1. And you plug in 1, so that's 1 plus 1, which is 2. So the right-hand limit equals 2. It's supposed to be right-hand limit. So the overall limit's got to be 2, since the left-hand limit equals the right-hand limit. So the answer limit as x approaches 1 of our function f of x is equal to 2, since the right-hand limit equals the left-hand limit. All right. So hopefully that makes sense. So we had a piecewise function. In particular, we were focusing on the limit as x approaches 1. Based on our conditions, it depends on which piece to use when involving 1. So I had a left side limit, a left-hand limit, and a right-hand limit. If those are equal to each other, then that means the overall limit exists and it's equal to whatever these ones equal to. And so for the left-hand limit, that's dealing with x values to the left of 1. So that's x values that are less than 1. So that's what's going on in purple. So I focus on just the top piece, x cubed plus 1, and just plug in 1. And that gives you 2. For the right-hand limit, that's x value to the right of 1, which means the x values are greater than 1. So that means I use the bottom piece, x plus 1. So still plugging in 1 into the bottom piece, x plus 1, it's 1 plus 1, it also gives me 2. So therefore the overall limit must be 2. All right, so then the next one, that was 23, this is the last one, number 25, cotangent of x as x approaches pi. So from trigonometry, you could write cotangent as 1 over tangent. So I'm going to write this as 1 over tangent of x. Now if you plug in pi, that's 1 over tangent of pi. Now what is tangent of pi? So tangent is sine over cosine. If you were to look at the unit circle, you'll see that at pi, the sine of the pi is -1 and the cosine of pi is 0. So I get -1 divided by 0. actually have that backwards. It'll be 0 over -1, which is 0. All right, so unit circle. You have the point -1, 0 at pi, cosines the x coordinate, sines the y coordinate. So it's 0 over -1, 0 divided by any number is 0, except if I were to divide by 0. So really this is 1 divided by 0, which we can't do. So like I did in the previous example where I graphed, so plugging in the value failed and there was no way I could, like in this one, where I can factor or rationalize to my advantage, so I ended up graphing it. Now I'm going to do the same thing for this one. There's no factoring I can do, there's no rationalizing I can do. So there's no factoring we can do to simplify the function, or rationalizing. So all else fails, I try looking at its graph. All right, and to graph it, so I'm focusing on f of x equals cotangent of x. You could write cotangent as 1 over tangent. So that's how I'm going to graph it, as 1 over tangent. So, and then make sure you're in radians. So I'm in radians. So y equals, I'm going to clear out what I had from the previous example. All right, so now I'm going to type in 1 divided by, and then here's the tangent button, tangent of x. And then I hit graph. And it gives me something like this, where these weird looking lines, these are the vertical asymptotes to the graph. Now you can format this, your window, so it's not just -10 to 10 and -10 to 10 for x and y. You can format it so that it fits usually the scaling by using radians. And I think I would go to zoom. Yeah, so we press zoom and you go to number 7, says Z trig. That makes the scaling in terms of radians, and it should be going from, I believe, -2 pi to 2 pi. So if I want to check, I can go to the x window. So x min, that's -2 pi. The x max is 2 pi. And notice I have these asymptotes. Now I can try to gauge where the asymptotes occur. Let's see, so I have an asymptote, so this is the axis. The asymptote is midway between -2 pi and 0. So there's a vertical asymptote at -pi. Since that's midway between -2 pi and the y-axis. And then there's another asymptote. So there's 0, and then 2 pi's over here. Then you have this vertical line. That's midway between these two. So that's going to be at pi. All right, so those are my asymptotes. And then now I just draw a general trend of the graph. So look, it has this cyclical pattern where it's like going down and then up like that. And it happens 1, 2, 3, 4 times for that cyclic pattern. So there's 4 cycles. So it goes like this. All right, yeah. Sorry, my drawing's pretty horrendous, but the y-axis is also an asymptote. So that's 1, 2 cycles. This would be the 3rd cycle. And then this is be the 4th. All right, so really just need a general idea of what the graph looks like. So I needed to know that I have these asymptotes. And I could draw more dashed line like that. -2 pi is an asymptote. And then 2 pi is an asymptote. So the asymptote, vertical asymptotes occur at multiples of pi. Like -2 pi, -pi. The y-axis is an asymptote that's technically 0 times pi, so that's 0, pi, and 2 pi, and so forth. So vertical asymptotes at x equals n times pi, where n is an integer. Now the question wants the limit as x approaches pi for cotangent. So the limit as x approaches pi. Which we know there's an asymptote, right? So just looking at it though, if I were to approach pi from the left, this thing is shooting down to -infinity. So the left-hand limit is -infinity. So as x approaches pi from the left, that's what the minus sign means. And then the graph itself, f of x, goes to -infinity. Now if I approach pi from the right side, the graph itself is going up to +infinity. So there are 2 different infinities that it approaches. So I would say x approaches pi with the plus sign, so approaches pi from the right, f of x approaches +infinity. So there are 2 different infinities. So that means the limit just doesn't exist altogether. It's not a finite value, and it's also not infinity. So these are different infinities. So limit doesn't exist. It's not finite, nor is it infinity. So obviously it's not finite, and since they go to 2 different infinities on which side, they don't go to a particular infinity. All right, so the answer that the book probably would have is doesn't exist. All right, and so that one I graphed it, and just to recap of how I graphed it, I'll start from the beginning. Let me clear out what I had before. So I typed in, so cotangent, I don't see a cotangent button on here, but I used a trig identity, reciprocal identity, that cotangent's 1 divided by tangent. So I did 1 divided by tangent, and then x, and then I graphed it. I've changed the window settings And this is always helpful for trig functions. If you change the format of the window so that it goes from -2 pi to 2 pi, you do that by hitting zoom and going to where it says z trig. If you did z standard, that makes it go from -10 to 10 for x and then -10 to 10 for y. So I hit that so that it scaled it. And from the scaling, now that I know that's -2 pi to 2 pi, this is the y-axis. This vertical line, that's an asymptote, happens to be in between -2 pi and the y-axis. So that's got to be -pi. This one's got to be pi. And based on the trend, it's going up forever. So this is an asymptote at -2 pi. Based on this trend going down forever, there's a asymptote at +2 pi. So that's that way I can get an idea for the graph, and they wanted the limit as x approaches pi. And just from my rough sketch, that's where I determined, well, if it's going to pi from the left side, that's in the green arrows, then it's going down to -infinity. Approaching pi from the right side, that's the purple arrows, it's going, the graph itself is going up forever to +infinity. So since they're two different infinities, there's not a particular infinity value that the limit equals. And also it's not finite. So I would say the limit doesn't exist altogether. All right, and that concludes the section 1.4.